Hi everyone, Mrs. Hanson here once again. Picking up with our lessons in Chapter 3, we are practicing binary ionic compounds. And so we're continuing looking at charges of positive ions with charges on negative ions and making sure we write formulas that represent binary ionic compounds. Binary, of course, meaning two elements. One of them will always be a metal, the other will always be a nonmetal. We'll learn that the metals are always written first. They carry the positive charge. They have lost electrons. The nonmetals will be written last. They are anions or negative ions, and they have gained electrons to form their charge. When we write out those symbols with their charges, we crisscross over the charges from top to bottom to find our subscripts to help us write electrically neutral compounds. We had said, for instance, if I'm using a calcium, and notice where calcium lives, it's in group 2A on our periodic table. All of the ions, we decided all of those in group 2A. Here's calcium. They have all of that in common. 2 valence electrons makes it a positive 2 charge. And so a calcium carries +2, loss of 2 electrons. And when we want to bind that, chemically bond to an oxide, remember how oxide lives in group 6A. And so any element in group 6A with its 6 valence electrons wants to gain 2 more to become like its noble gas. Oxide, when it forms an ion, will carry a -2 charge. Notice that a +2 and a -2 already balances to 0. 1 unit of a +2 electrically balances 1 unit of a -2. These charges are neutralized. So the chemical formula simply becomes CaO. Remember, we say the name of the first element just as it sounds, calcium. The last name, oxygen. The oxygen word does get changed. We take this last part off and end it with "ide." And then oxide, that's too many syllables. You'll hear oxide, just to kind of clean up that word. Oxide, calcium oxide, CaO. The charges are equal in magnitude. That's the +2 and the -2 balance one another. When they balanced, we don't need any further subscripts, CaO. But here's an example where we're using calcium again from before with its +2, and now I want to form a compound that binds it with chloride, -1. Now remember chloride, if I just quickly go back to that periodic table, remember it's your tool. Chloride is a halogen. It lives in group 7A, and we said all of these halogens with their 7 valence electrons need to gain 1 more to become like its noble gas. And so the charge looks like Cl -1. Notice now that a +2 and a -1 does not add to 0. It is not electrically balanced just yet. So that's where we say crisscross. Grab the charge, not the number with the, not the positive or negative, but just the quantity, 1. And we place it around and down. Take the quantity of +2, don't bring the charge with it, just the number, and bring it around and down. It would take 2 units of a -1 charge to balance 1 unit of a +2. So here's calcium. See how it's a +2 charge? Notice how each chloride at a -1 apiece, it took 2 units of chloride to balance the charge of 1 calcium ion. Notice that it took 1 calcium and 1 oxide to chemically balance a +2 and a -2. So this little subscript is what we use to tell you how many ions were needed to create a balanced compound. We would name this by saying the first name, just as it sounds off the periodic table, calcium, and then we end it with chloride. Notice the IDE ending, calcium chloride, chemical formula, CaCl2. And we're going to just keep practicing, practice, so that when we have all of this repetition, we become proficient. Letter A, let's write a formula between sodium and bromine. So remember our guidelines. Rule 1, identify the metal and the nonmetals. We'll write their symbols with charges, and then we cross over to find the subscripts. So here's where we find sodium. Sodium is in group 1A, and we know that all of those in the same column will carry a +1 charge. So for letter A, I write the elemental symbol sodium, Na, and I represent the charge it carries with a +1. Notice we're going to connect it to bromine. So go to your periodic table and find the element bromine. Notice that it's in group 7A. 7 valence electrons when you think about bromine, right? 7 valence electrons. It wants to gain one more to become like its noble gas, krypton. So gaining that extra electron makes it a -1 charge. Notice that a +1 and a -1 already balance to 0. So our formula simply takes 1 sodium and 1 bromide, and we write that as NaBr. We say the name of the first element just as it is off the periodic table. We say the name of the last element and end it with "ide." This becomes sodium bromide, NaBr. Should we try the next together? Here's barium and oxygen. So we're going to go to the chart and find barium. Here's where barium lives. Notice it is found in group 2A, and all of those found in the second family have 2 valence electrons. When it loses 2 electrons, it becomes like the noble gas xenon. They are isoelectronic. Barium will carry a +2 charge. It wants to chemically connect and bond, if you will, to oxygen. See where oxygen is? It's in group 6A. So think about that. Oxygen with its 6 valence electrons, it wants to add 2 more to make it become like neon's configuration, and gaining electrons makes it form a -2 charge. A +2 and a -2, oh, that's 0 already. So we don't need to crisscross because it came out electrically balanced. BaO, and naming it as barium oxide. Magnesium and iodine. So in letter C, we want to find magnesium. Let me just clean that up. And you know where that is? Right in the same column as where we found barium a moment ago in group 2A. We know that all elements in group 2A have 2 valence electrons. They're going to lose 2 electrons. Number 12 here, magnesium. When it loses 2 electrons, it becomes like the noble gas neon. So loss of 2 electrons makes it become a +2 charge. It wants to chemically bind to iodine. Notice that's in group 7A. That tells me iodine has 7 valence electrons. It wants to gain one more to become like the noble gas xenon, and when it gains one more, it becomes a -1 charge. Here we have an example, finally, where the positives and negatives don't come out matched. A +2 does not electrically balance a -1. So we crisscross. We bring the 2 around and down, and we bring the 1 around and down. Mg1, I2. To clean that up, we would write Mgi2. This would be called magnesium iodide. Hear the IDE ending. Now visually, magnesium with its 2 positive charges. It would take 2 units of an iodide, each at a -1, to balance those charges. So Mgi2, magnesium iodide. And then finally, how about letter D? Letter D gives us lithium. See where lithium is? Right in that first column, where with its 1 valence electron will form a charge of +1. And it's going to chemically bond to oxygen, who's in group 6A. Know what that means? Oxygen has 6 valence electrons. That's why it lives in group 6A. It wants to gain 2 more to become like neon. Gaining those 2 extra electrons makes it become a -2. Crisscross those charges to electrically balance those. So around and down, we get Li2O1. And we'll just clean that up, Li2O. Say the name of the first, just as it appears on the periodic table. That's lithium. And its last name becomes oxide. Think about that. Oxide is a -2. 2 minus is big, if you will, and lithium is only a +1, so it's going to take 2 lithium ions to neutralize 1 oxide. Li2O, lithium oxide. We're writing binary ionic compounds. Binary means 2 elements. Sodium bromide, barium oxide, magnesium iodide, and lithium oxide. Binary ionic compounds. Here's a question that asks us to consider molecular models. Which one would represent potassium chloride and which one would represent calcium chloride? Well, let's first figure out what these chemical formulas would look like. The element potassium is the symbol K. See it right here, number 19? So potassium chloride would be K +1 because every element in group 1 is going to have a +1 charge. And its last name is chloride. Remember what that guy is? It's in group 7A, 7 valence electrons, meaning it wants to gain 1 more, and when it does so, it becomes like argon, gaining an electron, -1, loss of an electron, +1. So our chemical formula between potassium and chloride is KCl. How about calcium chloride? Right next door to potassium is the element calcium. Potassium, number 19, number 20 is calcium. Notice its column is a +2, meaning it has 2 valence electrons. It wants to lose 2 electrons then to become like a noble gas of argon. So calcium loses 2 electrons to form an ion of +2. And chloride we found already to be -1. When we crisscross, bring those numbers around and down, and we find Ca1, Cl2, calcium chloride, CaCl2. Remember, calcium is a +2. It's going to take 2 separate chlorides, each at a -1, to balance 1 unit of a +2. Potassium is a +1. It's neutralized by just 1 chloride, a 1-to-1 ratio for KCl, where we had a 1-to-2 ratio for calcium chloride. Let's go to work and find those ratios. Notice here I have 3 green atoms, and I also have 3, I'll call those yellow, 3 yellow atoms. Well, that's the exact same number. I'll say that's a 1-to-1 ratio. A 1-to-1 ratio, same number of each atom. Whereas here I have 4 green atoms and only 2 purples. What I'm noticing here is we have a 2-to-1 ratio. And that's got to represent the calcium chloride, a 2-to-1 ratio. So for every 1 calcium, there's 2 chlorides in figure 2. For every 1 potassium, there's 1 chloride in figure 1. We have the 1-to-1 ratio. For every 1 K, there's a Cl ion. For every 1 calcium ion, I see twice the number of greens for chloride. Good work. When we name ionic compounds, those main group elements are just simply named for the ions that we stand for. Say the name of the element. Positive ions do not get changed. We just simply say the name of the positive ions. And if I write PT, you'll know I mean periodic table. So main group cations, the sodium ion, Na+, we're just saying the name of the element, and we put on the word ion to let you know it's charged. K+ is named potassium ion. Ca2 positive, calcium ion. Mg2 positive, the magnesium ion. Say the names of each ions, and then we'll give the symbols. So just as a reminder, if we have positives, we just say the names. But let's make a note here about the negatives. That's where I want us to remember that we change the ending to IDE. Alrighty, so let's try these now. S2 negative. Well, the element's name is sulfur. Sulfur becomes sulfide ion because I'm changing the ending to "ide" for the negative ion, sulfide. Letter B, I see Cu+1. Now remember this? This lies in the heartland of I don't know your charge by where you live. So remember, these are all requirements of the Roman numerals because they have a variable charge. So this is allowing me to kind of emphasize, I have to remember if it's a fixed charge, no Roman numeral. All the column +1s, no Roman numeral. All the column of +2, no Roman numeral. I know aluminum's a +3. I know that, no Roman numeral. And zinc, cadmium, and silver, we wrote in our notes as exceptions to the Roman numeral. Copper lives in the heartland of, I don't know what your charge is, so I have to tell you in its name. Notice this is called copper 1, and I'm going to put that in a parenthesis to let you know it's carrying a +1 charge, copper 1. Here's CS, that's cesium. Cesium lives in a column where I definitely know its charge. It's always, always, always a +1. So no Roman numeral because I know its charge. CESIUM, cesium ion. Not a variable charge, but a fixed charge. Roman numerals are needed for those metals that have a variable charge. Roman numerals are not needed for those ions that we know have fixed charges. The +1s in column 1 are fixed. The +2s in column 2 are fixed, no Roman numeral. Aluminum is a fixed +3, it never varies. Zinc, cadmium are always +2s, that's a fixed charge, just as silver is a +1. Cesium has a fixed charge of +1, no Roman numeral. Just like aluminum, we're going to just say the name of the ion, aluminum, and let you know it's carrying the +3 charge with the name aluminum ion. I called it iron. And SN stands for tin. Tin also has a variable charge. It is not found in the first family where fixed charges. It's not found in the second family of fixed charges. It's not aluminum, zinc, cadmium, or silver. So therefore, it has a variable charge. All the metals, as you did this little staircase here, all the metals up until the world of the, the border, when you hop over to the negatives, they have a variable charge. So I have to label that as tin 4 ion. Let's keep going. This one is called stannous. And did you know that stannous is actually the name here for tin, SN? Now if you didn't know that, I think that's okay. We used a Roman numeral to kind of help us with those names, but we did kind of have a chart, a few pages back that gave us those variable names. I was just trying to scroll through here to see if we could find those. All the little Latin names for the elements there, for the transition elements there. I don't see it. But anyway, stannous is tin. And so as I come here, I'm going to name this as tin. And then since I'm just reminding us that the lower would have the OUS ending, this would be SN plus 2. Stanic with the ic ending would be SN plus 4, representing the other possible charge on tin, tin 4 ion. All right, iodide. Here the ide, now I know it's negative. That comes from the element from iodine. Being in group 7A, we understand that it gains 1 electron, so it becomes I negative 1. Manganese requires a Roman numeral, so I put a little asterisk there. Let's do manganese 2 ion. See, manganese lives in the heartland of, I don't know your charge by where you live. You have a variable charge and thus requires the Roman numeral. So I'm letting you know this little parenthesis tells me to carry a +2 charge known as manganese 2 ion. The elemental symbol for lead you find here is I'm circling Pb, and the charge comes from its Roman numeral. That's lead with a +2. Here the ending of ide, that lets you know it's negative. Selenide, that's the elemental symbol Se. See where it lives in group 6A? Just envision what that means. You have 6 valence electrons. It has room to gain 2 more to become a noble gas configuration, and thus it ends up as a -2 charge. Let's name each of these binary ionic compounds. I would encourage you to pause the video and work ahead. Try these out. I put a periodic table here for your convenience so you can find the names of the elements. Remember, the last ones end with "ide," and double check. Does the metal require a Roman numeral? So that's kind of the last thing we check. I'm going to write that note here for you. Does the metal require a Roman numeral? And to answer that question, Roman numeral, there, I got it, spell it right. It does not get a Roman numeral if it's in the first column. Those are always +1s. It does not get a Roman numeral if it's in the second column. That's +2. Aluminum does not get a Roman numeral. It's always +3. Zinc, always +2. Cadmium +2. Silver +1. Every other metal that's to the left of this border, right? Those are always the metals to the left of that highlighted border I just made, require a Roman numeral in its name. And the Roman numeral is coming from the charge that it carries. So let's practice. Give them a shot. Come back with the video when you want to check. All right, letter A, Na. Na stands for the element sodium. So highlighted right here, sodium. Does sodium need a Roman numeral? And the answer is nope. It's in column 1. It has a fixed charge of +1. The element fluoride. Well, F stands for fluorine. We hear the ending change for the negatives. Sodium fluoride, NaF. MgO is the letter B. Mg is the element magnesium. No Roman numeral. It's in a fixed column of +2. So just naming that as magnesium, no Roman numeral required. The symbol O comes from the element oxygen. We end it with oxide, OXIDE, for the binary compound ending, magnesium oxide. How about Sr, Br2? Sr is the symbol for the element strontium, located right here where I'm circling in group 2A. That's a fixed charge of a +2, so no Roman numeral. Strontium. Br over here in the halogens, group 7A. Changing bromine to the ending ide, you get strontium bromide. Elemental symbol Li stands for lithium. Lithium is in a fixed column of +1, no Roman numeral. The elemental symbol O is oxygen. Changing its ending to "ide," we get lithium oxide. Letter E, Ti. Now look where Ti lives. It lives in the heartland of I don't know your charge. This is a variable charge. So now I find finally an example where a Roman numeral is going to be required. The first name is titanium, but part of its name is a required Roman numeral. And let me just kind of leave space, and we're going to work out the charge that it carries. And I wanted to emphasize, very critical, that the charge, not how many you have, but the charge goes inside the parenthesis. A common mistake a beginning student might make is looking at this subscript as a 1 and wanting to put a 1 inside the parenthesis. It is not telling me how many I have, but rather the charge that it's carrying. We have to play detective to figure out its positive charge. And to do so, find the negative ion that it's attached to. You see how that's an oxide? And because oxide lives in group 6A, remember what that means? 6 valence electrons. Oxide wants 2 more to become a noble gas. So when it gains 2 electrons, we know it's a -2 charge. Now think about an oxide, a -2 charge. And there's 2 of them in that formula. So we have 2 separate O -2s. That's a total magnitude of a -4. Our titanium has to carry a +4 charge to electrically balance 2 units of a -2. Titanium 4 oxide. Let me kind of stress that another way. Titanium was a +4, oxide was a -2. When we originally crisscrossed and would bring those charges around and down, we noticed we had Ti subscript 2 with O subscript 4. A formula unit, which is that basic building block of ionic compounds, right? That's called the basic building block. These must be in the lowest whole number ratio possible. In order to be correct, they must have the subscripts in the lowest ratio possible. So instead of having a 2 and a 4, they simplified that by a 1:2 ratio. It's still named titanium 4 oxide because that titanium's magnitude of charge is +4. Okay, that was a good one. TiO2, properly named titanium Roman numeral 4 oxide. One more in that set you wanted to check with me. Al, well, that's the element for aluminum. Aluminum, there, I spelled it right. Does aluminum require a Roman numeral? And you answered no. It's a fixed charge of +3, so no Roman numeral. We named that simply aluminum chloride. How'd you do? Oh, you'll get better and better with repetition. Here's some more. Pause the video. Don't cheat yourself. Pause the video and come back to check. I can see, boy, the vast majority, if not all, are going to require Roman numerals. These are transition elements written first. All right, letter A. Letter A stands for the element chromium. I know chromium lives in the heartland of a variable charge, so this requires a Roman numeral. The variable charge can be determined by the negative ion it's attached to. Chloride is a -1, right? So just think about what that means. We had CrCl3. If chloride is a -1 and there's 3 of them there, visually, do you see what that means? 3 units of this -1 chloride. we have just 1 unit of chromium neutralizing. It takes 1 positive 3 chromium to electrically balance 3 units of the -1 chloride. So what is the chromium charge? It's 3. Remember, this subscript is not the purpose of the Roman numeral. It's not how many you have, but it's the charge that you carry. Chromium must have been a +3 to neutralize chloride's -1. That's called chromium 3 chloride. We'll keep practicing. Here's letter B. Letter B, I see the element Pb. That's the elemental symbol for lead. See it right here? Pb. Lead lives in the heartland of having a variable charge. It requires a Roman numeral. So I'll leave a parenthesis as part of the name. The element S is sulfur. Ending in the IDE, you hear that called sulfide. Notice we have, just playing detective, we have to figure out what is the positive charge on lead that's balancing the charge on sulfur. Sulfur lives in group 6A, right under oxygen. So remember, that means it has 6 valence electrons. When it gains 2 more to become like the noble gas argon, gaining 2 electrons makes it a -2 charge. So what must the charge on lead be, knowing that we have a 1-to-1 ratio? If sulfur is a -2, and there's just one of them, lead also has to balance with a +2, and we have this 1-to-1 ratio, Pb +2, balanced by S -2. In the parenthesis goes the charge. This is known as lead 2 sulfide. How about letter C? Sn, that's the elemental symbol for tin. I'm going to leave the parenthesis open, and as we work to figure out the charge, that's what will go in. F is the elemental symbol for fluoride. So we have tin something. I have to work on that. Fluoride. Fluoride is a -1 charge. So what must be the charge on the tin to electrically balance 4 units of fluoride? So as I draw that out, I'm helping us visualize 4 separate F- ions. And I only have 1 Sn in the formula. Notice we have a 1-to-4 ratio, 1 positive. Well, that tin has to be 4 positives. Whoops. There, I have it back. 4 positives to balance the 4 individual -1s. This is tin 4 fluoride. Next one, PbO2. Oxide, we saw just a moment ago, is in group 6A. So I know that oxide carries a -2 charge. And do you see how there's 2 of them in the formula? So 2 units of a -2 charge. We have 1 Pb. Remember, Pb is our lead. I'm going to leave room in that parenthesis so that we can determine the charge. For every 1 lead, 2 oxides are chemically bonded. And the goal is to create an electrically neutral compound. Lead must be carrying a +4 charge to chemically balance the -2s from both oxygens. That's lead 4 oxide. Fe stands for the element iron. Fe is right here on your chart, so that's iron. I'm going to leave the parenthesis because iron has a variable charge and thus requires the Roman numeral. It's hooked to bromide. You see bromide here in group 7A, knowing that it's a -1 charge. See the ratio of negative ions. There's 2 units of Br negative bonded to 1 iron. The iron has to carry a +2 to balance the 2 individual -1s on bromide. Iron 2 bromide. You're doing good. Here's gold. Gold is Au. It requires a Roman numeral in its name. It has a variable charge. Let me leave that parenthesis open for a moment to include that in its name. Last name is chloride. Let's play detective and determine the total negative charge, and therefore working backwards we can find the charge on gold, Au. Chloride carries a -1. It's in group 7A. It gains one more electron to share the configuration with argon. So we have chloride, Cl negative, and there's 3 of them in that formula. 3 individual chlorides. Chemically bonded to just 1 unit of Au. It's going to require a +3 charge on gold to neutralize 3 individual -1 chlorides. The charge that it's carrying, gold 3 chloride. In your next set that you worked ahead on, these all had the same first name. They were Cu for copper. So I'm going to just get that written and make sure that I leave space in a parenthesis to indicate the charge that the copper is carrying. So we have to kind of play detective here and work backwards to find the positive charge that balances whatever it's attached to, a negative. So let's compare letter A, Cu2O. We know oxygen here in group 6A will carry a -2 charge. And notice that it has just 1 unit of a -2. Copper is just one of them, right? The subscript here is a 1. But I have 2 individual coppers. The subscript next to copper is a +1. Notice that it takes 2 coppers at a +1 to balance 1 oxide. So copper 1 oxide, Cu2O. But if you compare that to letter B, oxide, who's that -2, if I only see 1 copper in that, a 1-to-1 ratio of those ions, well, it was neutralized by copper's +2 charge. Copper 1 oxide, Cu2O. Copper 2 oxide, CuO. This allows me to emphasize the Roman numeral is the charge, not how many, right? So when I look at Cu2O, don't be fooled into thinking that that's the Roman numeral. It's not. It's telling me that I had a +1, 2 units of that +1 to electrically balance the -2. Letter C is attached to chloride as well as D. So let's compare the charges now for chlorides. Notice here I have a 1-to-1 ratio in letter C. Chloride is in group 7A. Gaining 1 electron makes it a -1 charge. So I have a Cl -1. And I notice that it's just being neutralized by 1 copper, right? That 1-to-1 ratio in the formula. So copper must be a +1, CuCl. However, in the next example, I'm seeing 2 individual chlorides with that ratio of 1-to-2. 2 chlorides, well, that's got to be balanced by a copper that's a magnitude of a 2 charge. It takes 1 copper at a +2 to chemically balance, electrically balance their 2 separate chlorides, each at a -1. Practice builds proficiency and it builds speed. The more we work examples, the easier they become, the faster you become. That's what proficiency and speed will do for test day. You'll finish on time and you'll finish correctly. All right, so let's keep practicing. Let's write a formula for tin, Roman numeral 4, oxide. The tin has the elemental symbol Sn. So I'm going to start by writing Sn. The Roman numeral indicates the charge, not how many you have, but the charge that it carries. That's a +4. Oxide is the element oxygen. We see that it lives in group 6A. Think what that means. 6 valence electrons, gains 2 more, giving it a -2 charge. When we crisscross, we have to write SN2O4. But that's not right yet, because A moment ago, remember that a formula unit must have the lowest ratio possible. That 2:4 ratio needs to be reduced. Cut it in half. A 1:2 ratio gives us the chemical formula for tin 4 oxide. How about sodium oxide? Now there's no Roman numeral there after sodium, but we don't need it. We know that sodium's a +1. We know that because it has a fixed charge living in column 1A. Sodium's elemental symbol is Na, and I know just by where it lives, it carries a +1 charge. I don't need a Roman numeral to tell me that. Here's oxide. We know it's in -2. When we crisscross, bring these around and down. Na2O1 simply becomes Na2O, sodium oxide. We're going to keep practicing. Here we have a mix of all binary compounds. Some of them have fixed charge, some of them have variable charge. That's why I see the presence or absence of a Roman numeral. Letter A is calcium. No Roman numeral after it, but I don't need it. I know calcium will be a +2 because it's in a fixed column of a +2 charge. Here's bromide. That's from the element bromine. I know that it carries a -1 charge just because it lives in group 7A. Bromine, with its 7 valence electrons, will add 1 more to become like a noble gas, making it a -1. When we crisscross, we bring our numbers around and down. Ca1, Br2. Calcium bromide, CaBr2. Calcium carries a +2 charge. Bromide carries a -1 charge. I can see that for every 1 +2 calcium, I am going to require 2 units of a -1 bromide, CaBr2. How about copper 1 iodide? Elemental symbol of copper, Cu. I wouldn't know its charge based on where it lives, so I see the Roman numeral. It's a +1 charge. It's chemically bonded with iodide. I, just like bromine, it's group 7A. So bromine, I'm doing iodide. I -1. Look at a +1 and a -1 is balanced. I don't need any further subscript, Cui. Ferric gives us the higher charge on iron. Ferric bromide I could name as iron 3 bromide, telling me that iron is a +3 and that bromide is a -1. I know that based on where it lives. Crisscross, bring these around and down. FeBr3, iron 3 bromide. Letter D, magnesium, who's a +2. Sulfide, that's the element S. Group 6A is a -2. That's 0 already. That's just simply MgS, magnesium sulfide. Chromium, +2. And chloride, -1. And we have a +2 -1. Bring those charges around and down. CrCl2, chromium 2 chloride. Remember, repetition over and over and over for drill work, and we'll have these. I'll pause the video here. In our next site, we're going to invite more players on the field. We're going to talk about polyatomic ions and using polyatomic ions to create what are called ternary ionic compounds. So come on back when ready with your polyatomic ion chart, a tool page provided in your note pack.